Hello there. So in this video, I am going to discuss about production scheduling using differential evolution meta heuristic. So what is a scheduling problem? Scheduling, we all know that scheduling is a decision-making process which deals with allocation of jobs to resources over a given period of time. So in manufacturing process, scheduling deals with finding the order of processing the jobs. So I mean that which item will be produced with which equipment or by which human labor at which point of time. So determining this is called scheduling in manufacturing industry. So the purpose of scheduling is to minimize the production time and cost so that the firm can maximize their efficiency and reduce their cost. So this is the purpose of scheduling in manufacturing. So if we see scheduling as a broad problem, then there are three sub-problems under the name scheduling. Those are loading, sequencing, and scheduling. When we are concerned with manufacturing industry only. So what does loading mean? Loading means to assign tasks to resources, and sequencing is to determine the order in which the jobs are to be processed. And in general, scheduling means actually both. Scheduling captures both the idea of timing and utilization of resources. So in manufacturing, as far as the factories and production floors are concerned, the scheduling problem can be different in a permutation flow shop or in a job shop or in an open shop. So what does flow shop mean? Let us first see about flow shop. So in flow shop, all the jobs have the same processing order throughout all the machines, but the order of jobs on each machine can vary. So if we go for exhaustive enumeration, then we will have to go through n factorial to the power m number of possible solutions. Now let us come to permutation flow shop. So this is actually a special case of flow shop problem where all jobs have the same processing order through the machines, but here each machine processes the jobs in the same order as the order of the processing order of the jobs. So this is the difference between flow shop and permutation flow shop. So there is a more restriction in permutation flow shop. That's why there we have to go through only n factorial number of possible solutions if we perform exhaustive enumeration. Now we all know that job shop is a specialized production process. So here where each job has its own routing through the machines, because the produced products are of much more variety. So there will be, of course, a hike in possible number of solutions. And in open shop and dynamic, these are actually more specialized production processes. So the number of possible solutions, so it will be much more. So we are interested in permutation flow shop scheduling problem only. So there are some general assumptions which are made for this permutation flow shop scheduling problem. So first, there is a very trivial assumption, that is all the jobs are available and ready to start at time 0. Secondly, this is a very important assumption that the machines are available throughout the scheduling period, because by stating this, we mean that we are not considering any downtime or any maintenance issues of the machines. Thirdly, each machine can process at most one job at a time, and each job can be processed on at most one machine at a time. Fourthly, preemption is not allowed. So no job can bypass any machine. The fifth point is that the processing times on each job on each machine are known and deterministic. And lastly, the setup times are sequence independent and included in processing times. It means that we are not considering the setup times explicitly. So those are already included in subsequent processing times. So now we will see that how the one permutation flow shop scheduling problem is formulated mathematically and how it is solved. So suppose there are n number of jobs which are to be processed over m number of machines, and Tij is the processing time of job j on machine I, where I runs from 1 to m and j runs from 1 to n, and these Tij values are deterministic as we told earlier. So here K be the order index. So what does this order index mean? Order index means that in a complete sequence or in one permutation, as there are n jobs, so there will be n spaces in one permutation. So each of those spaces are indexed by K. So this is actually the mean of K be the order index. So order index here refers to each position of the job of a complete sequence of jobs. So now we define our decision variables xjk, which is a binary decision variable which takes value 1 if job j is processed in kth order and takes value 0 in other cases. So this is another parameter we have defined qijk, which means completion time of job j on machine I in kth order. So given all these parameters and variables, now we can formulate the problem like this. So here our objective function is the makespan. So what does makespan mean? Makespan is the total time duration for processing all the n jobs on m machines. So this is the quantity we want to minimize. So this is the objective. This is our objective function. Now there are some constraints. So the first constraints represents the fact that a job does not start on a machine until it finishes processing on the previous machine. And the second constraint means that the predecessor of one job of each job has completed processing on that machine. It means that like jth job can be processed on ith machine only when j minus 1th job has been already processed on ith machine. So this is actually meant by this second constraint. So the third constraint means that each sequence position is filled with only one job. So this is also very trivial, that if we are to fill up n spaces with n jobs, then of course there should be one job at each position, at each space. So this is what this constraint means. The fourth constraint is that each job is assigned to only one position in the job sequence. So this is also very trivial, that if n jobs are to be assigned in n positions, then there can't be more than one job in any one position. So this is our fourth constraint. Now what is the fifth constraint? Fifth constraint means that when each xjk is 0, then the corresponding completion time parameter will also be 0. But the converse is not true. That is, when qijk will be 0, then there is no restriction that xjk should be 0. So to model this type of constraints, we use this m as a large positive value, and these constraints, and these type of constraints are modeled in this way. Now the last two constraints are variable and decision variable domain specific constraints, so which are non-negativity constraints, and this our decision variable should be binary. So now we come to solving this problem. So from the mathematical model, we can understand that it is a NP-hard problem, which means that this problem can't be solved within polynomial time complexity. So that's why we are making use of meta-heuristic techniques instead of going for exact algorithmic techniques. So differential evolution is one of those meta-heuristic techniques which are used to solve optimization problems with continuous decision variables. But here in this particular problem, this particular permutation flows of scheduling problem, we have seen that the decision variables are not continuous. Those are discrete. So actually, what is our decision variable or what is our decision vector? So this is our decision is to find out the optimal order in which all the jobs should be processed. So clearly, this is here the decision variables take discrete number of values. So that's why we can't directly use the differential evolution technique in to solve this problem. So we use a modified version of differential evolution, which is called as discrete differential evolution. So we are making use of this discrete differential evolution to solve our problem. So now we are representing our decision variable as xi comma k, and more precisely we are representing as xi, which is a vector of n variables, where each variable is indexed by k, and this superscript 0 means the generation. So as this is an evolutionary algorithm, we will have multiple generations, and these generations will be indexed by g, which will be rewritten in the superscript of the decision variable x. So first, what we do? First, we initialized our population of individuals in a random manner. So for initializing, we have to get some idea about the lower limit and upper limit of x, which is very much available in most of the cases. So given a lower and upper limit of the decision variable values, we can generate a number of individuals for our initial population randomly. Okay, so this rand k of 0, 1 means that we are generating random number from continuous distribution 0, 1. Now we already got one particular individual of the population. But the problem is that in this vector, all the elements are taking continuous values, which is not desired in this case. So that's why we use this largest order value rule, the LOV rule, so that the continuous values are transformed to discrete values. So what is the way? The way is that suppose if this is our random, this is one individual of our randomly initialized population, then we have to get the sequence. I mean, we have to get the discrete version of this vector. So how do we get the discrete version? So the process is that first we note down that what are the ranks of this of each of these values. So these ranks are contained in this phi I vector. So we are creating phi I from xi. So here the first entry of phi I is 4, means that 1.36 is fourth highest value in this xi vector. Here the second element of phi I vector is 1. This means that in second position of xi, we have the highest value of the xi vector. So in this way, we construct this phi I vector. And lastly, we get the final sequence or the sequence vector as pi I from this phi I. So how do we get pi I from phi I? So this is the formula, that at phi I comma k position of pi I vector, we will have the value k. So it means that in phi I, the first position there is 4. So in pi I, 1 will be in fourth position. Similarly, in second position of pi I, there is 1. So 2 will be in first position of pi I vector. So in this way, we construct the pi I vector. Now, once we got the pi I vector, there is no problem applying the usual steps of normal differential evolution. So now we go forward doing the other steps, which are called evolutionary phases. So the first step of the evolutionary phase is mutation. So we use mutation for global search in meta-heuristic algorithms. So here, let's see how the global search is done. So suppose there are two variables, x1 and x2. and in this variable space there are 3 individuals in the population, XR1, XR2 and XR3. Then from these 3 individuals we get a new individual after mutation, which is called the mutant vector V by this equation, XR0 plus F into XR1 minus XR2. So this is the difference vector XR3 minus XR2. We multiply this difference vector by F and get F into XR3 minus XR2. Now we add this vector with XR1 to get the mutant vector V. So till now we were dealing with the target vector X, which was initialized randomly. Now from the X's we get V, which are called the mutant vectors. Now we will see what are the next steps. So the very next step is crossover. So we use crossover for local searching in meta-heuristic techniques. So here, what does it mean? Suppose there are 2 variables, x1 and x2. So these were our target vector initially. Now after mutation, we got the mutant vector as v1, v2. Then after crossover, we can get either x1, v2 or v1, v2 or v1, x2 or x1, x2. This will depend on the random number generated for each of the bits. Here by bit I mean the variable. Each of the variable we will have to generate a random number. In particularly our case, we have to generate a random number for all the sequence positions or for all the orders. So if the random number is less than crossover probability, then so this crossover probability is a parameter which is to be mentioned beforehand. So if this is less than crossover probability, then there will be no crossover taking place and we will simply use the mutant vector as the test vector. Otherwise, we will use the target vector as test vector. So in this way, after crossover, we are able to get a set of test vectors from the target vectors and mutant vectors. Now, the next step is selection. So in one particular generation, we used to have 3 set of vectors. What are those? Target vectors, mutant vectors, and test vectors. Now we will select that which are the best. So which are the members that will go for the next generation. So in G+1th generation, we will choose the test vector of gth generation if the test vector of gth generation gives better performance than x vector of gth generation. Otherwise, we will go for the target vector only. So as this is a minimization objective problem, we are considering this, this sign is written as less than equal to. Otherwise, if in case of maximization problem, this sign would be greater than equal to. So these are the 3 steps of the evolutionary phase of differential evolution. So what are the 3 phases? Mutation, crossover, and selection. So we will continue to repeat these 3 steps till our stopping criteria is reached. So what is stopping criteria? Stopping criteria may be the number of iterations, or we may also set the stopping criteria as suppose for m number of iterations, our optimal solution is not changing. Then we will stop our algorithm there. So stopping criteria can be thought of like this. So this is all about the differential evolution algorithm, or more specifically in our case, the discrete differential evolution algorithm. So this is proven to give better result in most of in particularly these cases, the permutation flows of scheduling problem. So to summarize the differential evolution meta-heuristic technique, so first we initialize the population randomly, then we perform mutation, crossover, and selection. Then if stopping criteria is met, then we stop right there. Otherwise we continue to perform these 3 steps: mutation, crossover, and selection. So in this way, we can get rid of those NP hard problems But again, there is a trade-off that there is a possibility that we may not find the optimal solution always, but of course we will get a solution. I mean, a near optimal solution in most of the cases, if the number of iterations is more and all the parameters are set correctly. So that's all for in this video. Thank you very much.